Okay, so remember the idea. So the proof. Recall the idea, right? We assume, well, there was this fact that there exists a solution, x, to the problem. We just assume that fact that there exists a solution, and we take the singular value decomposition of it. Right? Suppose it looked like this. Say you do singular value decomposition, and then we let B be Q transpose AP, so that A was QB P transpose. Right? Right? And then the first thing we did was that we saw that this distance, which we're hoping to show, is right. Suffice to show that this distance was greater than or equal to this, and we said, okay, using this notation, we see that we can change this into B minus omega, the distance between B and omega, where omega is the central matrix in the singular value decomposition of X. Right? Right, and in step 2, we introduce this notation. Omega we wrote as this, right? This is the non-zero part, right? Right, because X is of rank K, so there's going to be this K by K matrix here, which is, and then everything else is zeros. Right? And we wrote B as, we split up these parts so that they would have the same sizes as those of the split here. Right? So this is a K by K matrix, and et cetera, et cetera. Okay, and then using that notation, we remarked that that B minus omega, the distance from B to omega in Frobenius norm squared was omega k minus B11 squared plus B12 squared plus B21 squared plus B22. Right, so this is just like a change in notation. Okay, and then what we saw was that that B12 had to be 0, that B21 had to be the zero matrix, and that B11 had to be omega k. Right? And that's basically where we stopped with B. We ended up with B looking like this. Right? That's where we ended. B. We figured out the structure of B. B has to look like this. Okay. B has to look like this, and so plus A minus X, the Frobenius norm squared, which equals this thing, is going to equal B22. B22 is Frobenius norm squared. Right? Because B looks like this now, so this is 0, this is 0, and this is 0. Okay? So all these things are 0, and we get this. Right? that's so, okay. So here's the claim that the Frobenius norm of B22 is bigger than or equal to the sum of the squares of the singular values, everything to the square, everything square rooted, right? And that will finish it up. That will be the end. Everyone on board with that statement? This is the end. Okay. So here's the proof. We'll use the singular value decomposition again. Say that B22 has a singular value decomposition that looks like this. Suppose that B22 has a singular value decomposition. Let U2 be the k by k identity matrix, and U1 down here. V2 be, again, the k by k identity matrix, and V1 down here. Okay. So then if we take B, right? If we take B over there, right, and we conjugate it, and we multiply on the left by U2, and on the right by B2 transpose, what do we get? Well, we've got the identity matrix here and here, right? Got the identity matrix here and here, right? So that's not going to affect. Right? We're going to have something like this. Right? The identity matrix is not going to. So this part of B, this part is not going to change, right? And this part is going to turn into U1 lambda V1T. Right. We're going to get identity matrix transpose. This, and then here we're going to get U1 lambda V1T, which is this thing here, just by how matrix multiplication works. So, now, what is that again? That is U2 that's going to be U2B. Remember what B was. B was QTAP V2T. Right. I'm just using what B was. This thing is B. Right. That's how we define B at the beginning. Okay. So what do you get? You get that A is this thing, and U2 transpose Q, and then V2 P transpose. Right, just inverting these guys and moving them over to the right-hand side. Right? Right. So U2 Q QT, U2 Q transpose A times B B2 transpose equals this thing. So what's A? Well, I'm going to just multiply, by inverses on the right and on the left, and to get A. Right? Okay. But look at this thing, right? These guys were orthogonal matrices. Right? Each of these guys were orthogonal matrices. These guys are also orthogonal matrices, right? So what we have here is this is up to the order of the singular values, up to the order of the diagonal entries of this thing. A singular value decomposition of A. Right? You've expressed A as this basically diagonal rectangular matrix here, and with an orthogonal matrix here and an orthogonal matrix here. Right. The only thing that it might not make it a singular value decomposition is that these guys here are in decreasing order. Right. So why do I say up to the order of the diagonal entries? This thing was from the singular value decomposition of X. Right. So these are all in decreasing order. This thing was from the singular value decomposition of B22. Right? So these are all in decreasing order. But you don't know that the whole thing is in decreasing order. Maybe some of the guys down here are bigger than the ones up here, and you have to reorder them. Okay. Are there any questions? People are looking either down or ask questions. Does that make sense? So we end up with this thing that looks like a singular value decomposition, right? A equals some matrix, and then there's this basically diagonal thing here, and then there's this other matrix transpose, right? Where this thing on the left is orthogonal, this thing on the right is orthogonal also, right? And I'm saying that there's only one thing that stops you from being a real singular value decomposition, and that is that maybe these things down the diagonal here are not in the right order, right? Certainly within each block, these are decreasing, and within this block they're decreasing. But you don't know, maybe some of the guys down here are bigger than some of the guys up here, and so they need to be switched over. Right? You'd have to switch the rows here to make it a true singular value decomposition. Okay, so this is basically a singular value decomposition of A, right? Right. So, what does that tell you? What does that tell you? What does that tell you? That's a rhetorical question. Sorry, you don't have to answer. What does that tell you? What does it tell you? That tells you that lambda then is going to have lambda, this guy down here, is going to have singular values of A down its diagonal. Right? This thing is singular value decomposition of A. So you know that these guys are singular values. The singular values of lambda are the singular values of singular values of B22 are the singular values of A, although maybe not in the right order. So that's why I'm not. You might think, why isn't he writing just k plus 1 through n? That's because I don't know, right? They might not be in the right. These guys might not be in the right order, so I'm just going to put dots there. Right? I'm going to call it lambda, lambda dot, lambda dot, lambda dot. So all these guys where the lambda dots are all in the, are all singular values of A, distinct singular values of A. These are all different singular values. We just don't know which ones they are. Okay, we just don't know which ones they are. Okay. So then, what's the Frobenius norm? What's the Frobenius norm of B22? What's the Frobenius norm of B22? Well, the Frobenius norm of a matrix equals the Frobenius norm of the central guy, right? Because multiplying by, on the left or right, by orthogonal matrices doesn't change the Frobenius norm. Right? That's what we saw last time. That, you know, multiplying by orthogonal matrix doesn't change the Frobenius norm. Okay. So, what equals this? Right? Well, what's that? That's going to be lambda dot squared plus lambda dot squared to the 1/2. Right? Okay. But that's bigger than or equal to lambda k plus 1 squared plus lambda n squared to the 1/2. Because there are n minus k of these guys. There are n minus k of these guys. Why? So I'll let you do this last exercise. Why is this bigger than this?
Why is the top one bigger than the bottom one?
Yeah. Why is this thing guaranteed to be bigger than this and thus close it for us? Because they're in decreasing order. Right? They're in decreasing order, so these guys are the smallest. Right? So if I take the n minus k smallest guys and I look at the sums of those squares, well, if I change these to other guys, it's not going to get smaller. At worst, it'll be the same. Right? It'll you know, if any of these are not here, it'll get bigger. Right? It could get bigger. Okay. So because these are in decreasing order, you know, I've got n minus k of these guys, and so this is going to be less than or equal to that. Okay. And that's the end, right? You see that that's the end, right? We see that that this equals this, right? So the distance to the matrices of rank k or less is actually the sum of the squares of the singular values greater than k, everything to the 1/2. Okay. And thus, the matrix we create out of the matrix we create using the singular matrix, and by truncating the central guy to the first k singular values, is the rank k, the best rank k approximation. Okay, so that's what this gives us. It gives us the best rank k approximation. Ask questions. I feel like some of you are maybe not quite getting it. Yeah, John.
I don't understand where you're exactly getting this lambda from. What does lambda represent?
So we reduce the problem down to this, right? That we're trying to find the distance of A to the the closest rank k matrix. closest rank K matrix, it turns out to be this thing. Okay, that turns out to be this thing here. Lambda is part of the singular value decomposition of this thing. Okay, so you say, well, you know, what is this? We're trying to get that the Frobenius norm of this thing is bounded below by this constant, and so we take a singular value decomposition, and lambda is just the central part of that. So it's the singular values of B22.
Yeah.
So yeah. This is the singular values of B22. But what turns out is that the singular values of B22 are singular values of A. Right? That's this point here. So the singular values of B22 are singular values of A. Right? So all these guys in lambda have to be singular values of A, and that's what gives it. Okay. Other questions? Teresa, are you all right?
Yeah.
Okay, it's pretty complicated, and I think maybe people since we've you have to sort of remember what we were doing last time. If you're not getting it, that's okay. Don't worry. Just go back and think about it. Go back and try to connect it together. Go back and try to connect together, and if you can't, then just come and ask, and I'll clear it up. Okay, so so that's the end of the course. That's the end of the course. That's the end of the course. So yeah. You guys clap. Actually, back in Princeton, we always clap at the end of every class. Every single class, at the end of the class, we'd always clap for the professors. Yeah, that's just how we did it.
Would you prefer that as professor?
It's not necessary. It's nice, but it's
maybe
nice.
we should start doing that.
I mean, it's a nice tradition, certainly. Certainly,
try
the
it.
professor does try pretty hard in general. I mean, you don't have to clap if you don't feel like it. Like, this guy didn't try that hard.
How professors? Were there ever like standing ovations, or was it
No.
generally like the same amount of clap?
No, it varied.
So if like if a professor did a horrible job, it would just be like a.
No. There was always at least polite. Applause, and sometimes more than that.